one giving us the keynote. Okay. The keynote for that June edition was given by Dr. Ishewon. Okay, and we had an overview of HPC in the African space, which was presented by engineer Mrs. Sweet Williams. And John Wedging also gave us a shot on the available infrastructure within the FedGen group and the Capicase as a whole. Now we have come to the July edition, and just as the Emir has rightly said, thank you all for keeping faith. And we're very optimistic that today's edition is going to be better. June edition was the best we have had. So I'm also very optimistic that today's edition will be really, really awesome as well. So Dr. Damilola Oshin is the facilitator for today, and it's going to be a continuation of what he started. He has done the first and second shot on the same topic, so he will continue from where he stopped, she stopped rather. And I'm sure there's also Engineer Gabriel Shobola, who is going to provide hands-on in order to see how what Dr. Oshin is teaching theoretically, how it can be applied within a practical context. So this is just to set the ground for today's tutorial, and I'm hoping that we are going to have the best of time as always. So I welcome everyone. Thank you very much for listening. Okay, so over to you, Comfort.
Thank you so much, sir.
Okay.
Yeah, so we are moving to the business of the day. Okay, so I'll call on Dr. Oshin now. You have 45 minutes. Thank you.
All right, good afternoon once again, everybody. You are welcome to the monthly advanced research tutorial for today. And well, not just today, for the month of July. And like Prof. Adetiba mentioned, it's a continuation of the topic we've been on. So we started with, it was on sequence modeling, really. And we had the first and second tutorial sessions on this. And today we'll be focused on the practical of this topic. So I'll just give like a recap of sequence modeling, really, and then we'll have something more practical, hands-on by Mr. Gabriel Shobola. All right, so okay, yeah, sure. All right, so let me share my okay. All right, so to bring us up to speed, once again, the theme for this series is mathematical foundations of artificial intelligence, and we've been looking at sequence modeling. And today, I'll be speaking as well as Mr. Gabriel Shobola. All right, so I just want to do a quick recap of what we've been talking about. All right, so sequence modeling Okay, so yes, so I wanted to do this because this is the third session on sequence modeling. So can someone tell us from, our live audience and those online, can somebody tell us what is sequence modeling? What kind of, yes, let that be the first question. What is sequence modeling? You can raise your hand if you're online and you want to give a response, or if you're here live, you can also indicate what is sequence modeling. Okay, Comfort, you want to? Okay. Okay. I can't see all of the online audience out there. Is this everybody?
Yes, so, do you want me to call some people
Yes.
for you?
Please call somebody.
Okay, so I have Omotola Idowu. Please, can you unmute yourself and answer us if you're there? Omotola Idowu. Okay, so if Omotola is not there, can we have Wisdom Owoyemi? Mr. Wisdom, please unmute yourself.
Good afternoon.
Good afternoon, sir.
Yes.
Yes.
Sequence modeling, I'm actually not familiar with it, but I can make an attempt.
Please go on.
All right, so sequence modeling is the ability of a computer of a computer program rather, to model and interpret or make predictions about a particular event. That's
Okay.
yes, from a basic knowledge
Sorry,
of
can you
sequence
take that
modeling.
again? Wisdom, can you take it again?
All right, so I said it's the ability of a computer program to model, to predict, and to interpret a particular event.
Okay, all right, thank you. Can we have a second try?
We have other people here.
Yes.
So, Mr. Dari.
All right, thank you. Mr. Dari, what is sequence modeling?
Okay, I feel it's a class of machine learning where the order of the input to the model is important.
Okay, all right, thank you. Thank you very much, both of you. So, once again, sequence modeling deals with modeling sequential data like speech, text, DNA sequences, and other related data. So in this type of model, like Gary said, the order is important, right? The order is important. And at the first tutorial, I presented or I mentioned about four types of models used for sequence modeling. The first one is right here on the screen, RNNs. So the other variants, can anybody remember them? There are four of them typically used for sequence modeling. So can we have 1, 2, 3 persons remind us of the other three types of models used for these kinds of problems? Who wants to try? Yes. Person should mention one.
My name is Julius. I think LSTM, long short-term memory.
All right, thank you very much. Yes, somebody else? Udeme? a type of sequence model apart from RNN, and then someone has mentioned LSTM.
Yeah.
No. Okay, Mr. Shobola wants to, oh, okay, Omotola Idowu. Yeah.
Okay, good afternoon, ma'am. Convolutional neural network, CNN.
Okay, thank you. Oh, that's not part of, it's not part of them. Wisdom, did you want to say something? It seems like you're unmuted and I'm not sure.
Yes, we have okay, I think it's already recurrent. That's what I wanted to say.
Which one? Okay, recurrent.
Current rather.
Oh, okay. So we mentioned that. So you have recurrent neural networks, you have LSTM, you also have GRUs, the gated recurrent units, and then the last one. So the last one, let me describe it. So let's see if anybody can mention the name of the model. So that's what ChatGPT uses. The last one. Exactly, transformers, yeah. All right, so those are the four models used for sequence modeling typically. Okay, so yeah, so this just gives examples of sequence data, the types of problems that you would use sequence modeling for. The first one that you have there, speech recognition, will be the use case for today. And that's what Mr. Gabriel Shobola will be, that's what we'll be presenting to us, how sequence modeling applies here. Okay, so you have music generation, sentiment classification, so here it says there's nothing to like in this movie. And then, you can see the output there. Excuse me, you can see the output there where you have a 1-star rating. So, and then you have DNA sequence DNA sequence analysis, machine translation, and video activity recognition. All right, so we went through a couple of application areas. In the first tutorial. Okay. So in engineering, this, of course, there are other application areas, but these are some application areas here. And like I mentioned, we'll be drilling in on speech recognition in particular. Okay. All right. So at this point, I'll just hand over to Mr. Shobola. I'll hand over to Mr. Shobola to take off from this point. So he'll be sharing with us. These are still introductory slides, but he'll be sharing with us, like I mentioned, the specific application speech recognition as it relates to sequence modeling. Okay, so perhaps at another time we could have a bioinformatics based application area. But for today we are focusing on speech recognition. All right.
Good afternoon, everyone. So, my name is Shobola Gabriel. So, I'll be speaking on application of sequence modeling, how it's used in for speech recognition. But before that, what we have before us is application in engineering. So here we have the first application there, the natural language processing. Before that slide, we have some application of it. There we have natural language processing, we have speech recognition, we have speech synthesis, we have time series prediction, we have discrete time signals, and we have unified modeling language. So these are areas where it's applied in engineering. Now, the first one, the natural language processing actually deals with machine translation, text-to-text conversion, sentiment analysis, and we have text summarization. The machine translation is a device or a speech or is a resource that can actually translate text from one language to text in another language. For instance, I can say I want to convert text from Igbo language to text in English. So the foundation behind that, the model that is used to actually achieve that is actually called the sequence model. So we have some algorithms that are used by researchers to actually fulfill that. So the second one there is sentimental analysis, which is for rating. As we see in the previous slide, I'll flip back a bit. In the previous slide, that's slide 4, we can see the sentimental analysis there. There is nothing to like in this movie. And the output there, the input there is a sequence of text that is given that we have there. And the output there is an integer that's actually rated by individual. So it's a value. So this kind of sequence modeling is actually carried out in the area of natural language processing. So the second one there with the speech recognition. The speech recognition is a tool or is a speech resource that actually takes input speech, and the output of such system is a text. For instance, I can speak. If I have my speech in English as I'm speaking now, I can have the English text equivalent of my speech. And that is what a speech recognition does. It recognizes the speech, my speech, and give me the text equivalent of my speech. So for the speech recognition, which we are going to be seeing later on, we said that in the conventional approach to modern ASR, we said we have some algorithms that are used. We have the Palm-Welch algorithm, we have the forward algorithm, we have the backward algorithm, we have the Vitabi algorithm. So with the Vitabi algorithm, the forward algorithm, we're going to be seeing how they are explored, or how they are used or utilized in speech recognition. And we have some other models like the Gaussian-Mixture model, we have the Eddy-Markov model. The Gaussian-Mixture model actually works similarly to K-means clustering. What they actually use it to do there is to cluster speech features before we now use the Eddy-Markov model to get the decoding sequence of text that are equivalent or that is equivalent of the speech waveform. So here we said compared to the conventional approach that involves the acoustic model, language model, and lexical model, sequence model have the encoder functioning as an acoustic model, decoder functioning as a language model, and some state-of-the-art techniques like the attention mechanism. Now, what researchers use at present is what we call the machine learning approach, that's the deep learning approach. So for the deep learning approach, for sequence modeling, we said the other time, we have the recurrent neural network, we have the long short-term memory, we have the bidirectional long short-term memory, we have the gated recurrent units, and we have the latest one, which is called the transformer architecture. So the transformer architecture is actually developing is improving the efficiency. I mean, it's trying to improve the efficiency of the previous one that we have, the recurrent neural network and its variant. That's where the transformer architecture. And what are those things that are used by the transformer architecture? We have what is called the attention mechanisms. We have what is called the positional encoding. So these are some of the techniques that are used. So in the next classes, we will be looking into that. But today, we want to look at the statistical approach. That's what gave rise to this machine learning approach. Because this machine learning approach, they actually developed from using the statistical modeling. So for today, we'll be looking at the statistical sequential modeling for speech recognition. And there we'll be talking about, we'll be using the Eddy-Markov model, the Vitabi algorithm. And in the next slide, we have the time series prediction. We have time series data like the weather data is another area where it's actually used in engineering. For instance, I want to make weather forecast. what will be the weather of today, knowing the weather of yesterday. So we can make prediction of that, which is also part of what we'll be looking at for speech recognition, how it's explored in speech recognition. And of course, we have discrete time signals, so we can model the speech waveform. For instance, we can model the vocal tracts of our voice. We can model it using a linear time varying system. And so that's one area of speech of sequence modeling in engineering. And of course, there are properties such as the stability, the memory, the linearity, the causality. They all depend on the associated series. And of course, the last one there, we have the sequence modeling that shows the sequential order from the inputs from the beginning to the end, how one input leads to the other. That is where we have the unified modeling language. So now, probably, so we want to look at sequence modeling for automatic speech recognition. So when we talk about automatic speech recognition, like I said before, we also call it speech recognition. Is a model or is a tool that actually recognizes the speech. That is, you feed it with the speech, and what you get is the text equivalent of that speech. So for speech recognition, we have some models that are used to actually achieve that. We have what is called the Gaussian mixture model. We have what is called the hidden Markov model. So for the Gaussian mixture model, so the process, I'll just give us an overview of the speech recognition. So how the speech recognition works is this. So we have a speech, we have our speech. Let's see my speech as I'm talking now. So what I'm going to do now for me to use my speech, I'm going to carry out what is called processing of my speech. That's pre-processing of my speech. So what I'm going to do there is I'm going to extract what is called the Mel spectrogram features of my speech. So that is actually what is used for training. So the Mel spectrogram is a frequency representation of that speech. So once I extract the Mel spectrogram of that speech, then the next thing I do there is, and now because like in those days, what they use is they use something like some rule base, such that when they see some speech features, they already know that the speech feature is actually related to a particular phoneme. Now, what do I mean by phonemes? The construction of words actually starts from smaller words, or let me call it group of letters. For instance, A, sheep. That's SH, as in church. So each of these, we call them phonemes. So there's also what we call folds. Now, for phonemes and folds, there are two different things entirely. Phonemes is actually spoken by phonemes, that's PHONEME. It's actually spoken by the dialect, by the native speaker. For instance, I can say, maybe I have a particular word. Let me just give an illustration. Let's say I have a particular word, we speak in a particular, like the British representation of a particular word. We can have different pronunciation of that word if an American is to speak that particular same word. So in such a case, having different pronunciation for that particular single word, we can call that folds. So each of those words, each of those variants of pronunciation, we can call them folds. While that particular single pronunciation spoken by the dialect, by the native speaker, we call it phonemes. So each of those phonemes, they are actually grouped. We can group them together. By the time we join them together using dictionary, we mix them together using dictionary. So by the time we mix them together, we construct words from it. Maybe B, A, T. B is a phoneme, A is a phoneme, then T is a phoneme. So we join them together, we construct a word. So what the Gaussian mixture model will now do is, once I have in my speech, so for instance, if I speak now, if I say, this is virgin. Now, this, we can get the phoneme like, or let me use a very simple word, like transcription. In English, if you check your Longman dictionary, for instance, we have the transcription written in slash. You see the transcription will be between two slashes. That's the beginning and the end. So what the Gaussian mixture model will do is to group each of those speech features. It will cluster them based on their attributes, based on their similarity. That is what the Gaussian mixture model will do. So once it clusters them, then the next thing there is for us to use the lexical model. We use the lexical model, that's the dictionary. The dictionary will now construct words from those phonemes. So once the lexical model, which is the dictionary, constructs each of those words, we now use the language model. The language model there is where we can, instead of this language model, we can use the transformer to actually do that. What will it do? The language model will now tell us that is it going to be a 2-word pronunciation, or a 3-word pronunciation, or a 4-word pronunciation. And it also constructs the right orderly arrangement, the right order of words that is actually needed. Maybe, for instance, this is Persian lab. Maybe that's what we need, and not this Persian lab. I hope we are getting it. So that's what the language model, because sometimes when we speak, for instance, we can use, let's say walk, like it walks, we actually come into play. And that's why most times they actually use the transformer architecture to actually do that. And that is where what is called the positional encoding. Because the positional encoding, we actually encode each of those words, we give them different position, so such that based on the context at any particular time of time, we always put them in the right order. Then where does the hidden Markov model, where does it come into play? Hidden Markov model is now used for decoding the right, because sometimes if you use the language model and want to decode, because for instance, if I say if I speak a word as I'm speaking now, let's say my speech is my speech. Now, if I want to decode it, I'm going to have this is my speech, is 4 words. It's having 4 words. So if I want to do the permutation of that, I'm going to be having different permutation of that, right? This is my speech. If my speech is, and so on and so forth. So where the hidden Markov model now comes into play is to decode the right sequence of words, or the right string that is replica of that speech. That is where the hidden Markov model. And of course, the correct sequence there is the one that has the highest probability. We always compute the probability, which you are going to see in the course of this training. So then we also said that we have on the next slide, we have some models that are used for, some machine learning model for speech recognition. There we have connectionist temporal classification. We have recurrent neural network transducer. We have attention-based model. We have recurrent neural network transducer with attention. These are actually some of the models, sequence modeling, that are used to model speech recognition. We can see that the attention mechanism, like I said before, the attention mechanism is actually it's like a filter. It can be likened to a filter, such that how much a particular, for instance, if I have the ball is there. Now, let's say I want to predict now. So each of those previous, the ball is there. Each of the first previous 4 words, we have certain amount of contribution to the prediction of now. So that is where the attention mechanism actually come into play. So it's going to give each one of them attention score. So what score is this bringing in to predict now? What score is bringing in to predict now? That is where the attention mechanism is coming to. The encoder, of course, is the input that takes the input raw speech, and the Bell spectrograms feature representation of speech goes into the encoder, and from there it goes to the attention mechanism like a filter, then it goes to the decoder, and from there you can do softmax activation there to get the final output. So we have different variants of them there. And on the next slide, we have sequential modeling in detail. So the first we want to look at there is the hidden Markov model, Markov chain. So what does the hidden Markov chain, what does it talk about? So what it means is that what's actually saying is that you want to predict the future. The information we have in predicting the future is actually in the past. In the immediate past. That is, if I want to predict what will happen today now, I don't need to go deeper into the future to look for information to predict the present. I can use yesterday's information to predict the present. For instance, if you look at that figure 6, we have sunny, we have cloudy, and we have rainy. If you look at the arrow very well, from cloudy to sunny, we have 0.2 pointing from cloudy to sunny. So what it means is the probability of each of them actually represent probability. What it means is the probability of sunny given cloudy. Probability of sunny given cloudy. So take where the arrow is coming from as the starting point. So the probability of sunny given cloudy is 0.2. The probability of cloudy given sunny is 0.3. I can also say, so it's also possible that we traverse, that we move within the same states. Here we have 3 states in the Markov chain. So if within a state, within cloudy, for instance, I can say probability of cloudy given cloudy is 0.3. That's the meaning. That's the bottom left hand side of that figure 6. So another thing we need to take into consideration there is, if you look at that C, for instance, the cloudy C, for instance, all the arrow that comes out of C, we have 0.5 coming out of. That's probability of rain given cloudy. We have 0.2 coming out of it. Probability of sunny given cloudy. And probability of cloudy given cloudy is also assumed to be coming out of it. If you have these 3 probabilities, it's going to give us 1. Then if you also check probability, if you also go to the area of the sunny, can somebody tell us the probability, the 3 probabilities coming out of the sunny states? Can anyone tell us the probability, 3 probabilities coming out of the sunny states? Anyone in the house? Coming out of the sunny state, the 3 probabilities coming out of the sunny states.
Who wants to try? So don't just say the value. Say, from one state to the other, the different state, the transition of states, and then the probabilities.
Okay, do we have anyone, physical participants? Okay, so we have, sorry, please.
Thank you very much. So from figure 6, the transition from sunny to raining is 0.3.
From what, sir?
From
Sunny?
the sunny state to the rainy state is 0.3. And then the transition from sunny state again to cloudy.
0.1.
Okay, 0.1, sorry. 0.1. And then from sunny state to cloudy state is 0.3. And the transition from sunny to sunny is now 0.6.
Yes.
All right, let's clap for him. Thank you very much.
Have online participants. So this doesn't just have to be like, this is not a presentation. So this is a training session. Let us know if you're still with us, if you're lost, so we don't just speak. Please, online participants, can you unmute yourself if you're still with us, if there's anything, please, so that we'll make this very, very interactive, not just presenting. We're not presenting. We want to learn. We want everyone to be carried along. Please, are we together? Online participants, please.
Yes, ma'am, still here.
Yes, we are still here, ma'am.
All right, thank you.
So there we have 3 probabilities coming out, or 3 transitions rather, coming out of sunny. That's probability of raining given sunny, that's 0.1. Probability of sunny given sunny, that's 0.6. And probability of cloudy given sunny, which is 0.3. If you had these 3, we have 1. If you had the 3, you have 1. So actually, this probability is what we call conditional probability. So, but we'll not be looking into that today. Is I believe we have knowledge of Bayes theory with conditional probability. So this is an example of a practical application of this is this. I can say that from this diagram figure 6, I can say the probability that today's weather will be sunny, given that yesterday's weather was cloudy, is 0.2. Do we get that? That's a typical illustration of that. I can say the probability that today's weather will be rainy, given that yesterday was cloudy, is 0.5. Do we get that? So each of these probability, you can see that as a transition from one state to another. So these are 3 states in the Markov chain. So each one of them, each of those states, each of those probabilities, we call them transition probability. each of them, we call them transition probabilities, and we can extract them onto a table which we call the transition matrix, which is so here on the next slide we can see where all the probabilities are extracted. You can see all the probabilities are extracted. I will say each probability is a conditional probability given as probability of x given y, which depicts conditional probability of x given y, which is probability of traversing from y to x. That's y is the reference point and x is the destination. So here we can see all the probabilities. Probability of sunny given sun is 0.2. Probability of cloudy given rainy given cloudy is 0.5. Probability of cloudy given cloudy is 0.3. So you can see that in that sequential order, if you have each three sets, 3 rows, you are going to have 1. If you pick the next 3, you have 1. The next 3, and we also have 1. So application. So the application of the above in weather forecasting can be, for instance, taking the left-hand side of the diagram, that's what I just said now. We have cloudy and sunny. So cloudy state can be taken as the present day weather condition, and the sunny state is taken as the future weather condition. So the question will then be, what's the probability of tomorrow being sunny given that today is cloudy? Who can answer that question? What's the probability that tomorrow will be sunny given that today is cloudy? Tomorrow will be sunny given that today is cloudy. What is the answer? That is 0.2. All right, so we can move on. So I believe that is very clear to us. So here from the hidden Markov chain, we have some attributes that we use to, parameters that we use to characterize the hidden Markov chain. We have what is called the transition probability, and we have what is called transition matrix. Transition probability is what we just saw from that from the trace diagram of the hidden Markov chain. So there, we said transition probability will model using equation 1. You can see what you have in equation 1 there. Probability of z of k of 1 equals to j, given that z of k equals to I. So you can see that in the first part of that conditional probability is k plus 1. And the second part, where the reference point there is just k. So why are we using that? Because the future one, where we are traversing to, is as to be at one time step higher than the previous step. That's the reason why we have 1 there. We can also say probability of z of k equals to j, given that probability of z of, okay, maybe I should not say this. Let's assume I want to change that equation 1. I don't want to use k plus 1 as the starting point for that k plus 1. I want to use k. So what would be the subscript for z of k? That's k minus what? K minus 1. So that is very fun. So, and of course, we have our table there. We have our matrix in figure 7 there. The transition matrix is not difficult. The interpretation there is for the transition matrix, the top row there where we have the sunny, cloudy, and rainy on the top. That's where we traverse to. That's the destination. While the column that we have on our left-hand side is the starting point where we are traversing from. So I can interpret it as probability of sunny given sunny is 0.6. I hope you are taking notes. Probability of cloudy given sunny to be 0.3. Probability of rainy given sunny is 0.1. Probability of cloudy given cloudy is 0.3. Probability of rainy given cloudy is 0.5. I hope that is very clear. And of course, if you sum all the probabilities horizontally per row, you are going to get 1, which I explained initially. So this is just a brief review of this transition matrix. So here we said application. We said with automatic speech recognition, the squares of word or string W, that is the language model is modeled as this Markov chain state, where the probability of occurrence of each word in the word sequence is known and used to calculate the sequence with maximum probability for observable extracted feature X.
Hello, Shobola. I think you are running too fast. You are doing as if you are doing a seminar presentation.
Okay, sir.
Make it tutorial like and try to get feedbacks. Is that okay?
Okay, sir.
Yeah.
Thank you, sir. So in speech recognition, now if you go back to that figure 6,
So on that figure 6, we have sunny, cloudy, and rainy. So let's say, for instance, I have the speech is the ball is here. Like this say 3 states now. 3 states markup chain will be modeled using 3 states word string. Like this is John. This is John, that's 3 states word. But this is John, we have different orders. For instance, if I want to arrange this is John, for instance, I can say this is John. This John is right. John is D, right? So how many order do we have there? 3, right? So we have 3 order, right? So, and of course, this is just the markup chain because we have what is called the ED markup model. For the ED markup model, we now have what is called the observation states. So the observation state there is the speech features which we cluster using the Gaussian mission model. So each of those, so for a particular feature that we have, what is the phoneme or what is the word string equivalent of that feature? Do you understand? Let's, for instance, now let's assume that we use letter X1, X2, X3. We have feature X1, X2, X3. We now have this is John. This John is, and so on and so forth. So, which among those 3 sequences is actually a replica of that speech? You know, when you speak, you will not be saying the word string equivalence. We get that now. So what they do first is to get the phoneme equivalent of those speech, and they use some algorithm like the forward algorithm, the backward algorithm, the backward algorithm to actually transition from one state to the other, such that from phonemes they develop words, and from words they develop sentence. So what is the word string that is replica of that particular feature? We are going to see in the later on. So how do we decode that particular sequence of words? So the sequence of words that is replica of that speech is actually the sequence of words with the highest probability, which we are going to see. That is where the Vitabe algorithm actually come into play. That is one application of this Markov chain, along with the hidden Markov model. So on the next slide, we have the hidden Markov model. SEG is a statistical method for development of acoustic model. The acoustic model there, we are talking about the Gaussian mixture model. So how do we cluster each of the features, each of the phonemes found in the speech features, such that we now use the hidden Markov chain to actually model them in order to decode the right word. And that's where you have the Vitabe algorithm. We have the Welch expectation maximization algorithm. So it was developed by Andrew Markov, and of course, it's used for in a lot of places. We can use it for weather patterns, finance, music, language, speech recognition, and written recognition. And we said, according to the model, knowledge of the present is enough to predict the future. We don't need to go far back in order to predict the future. So the hidden Markov model is a combination of the Markov chain that we just left now and some set of observable states. So when we have those observable states, we should be able to tell the sequence within the transition states that can give us that or that is replica of that observable states. So here they use the word hidden Markov. This is where the hidden Markov, the word hidden actually come into play. Now, if you go to the next slide, that's figure of H.
Sorry, Mr. Shobola, please can you repeat that again and this time around slowly so we get it?
Okay.
Thank you.
So if you look at the Markov model, if you look at it says the knowledge of the present is enough to predict the future. Now, if you look at that word hidden, the word hidden there is actually from the transition states, which we are going to get from this figure 8. The word hidden, look at that figure 8 very well. Now we have stats, we have rainy, we have sunny, we have walk, we have shop, and we have clean. So the start there is telling us the starting points for each of those transition states. Now, in the middle, we have transition states. We have, it's a two-state Hidden Markov model. We have rainy and sunny. So the rainy and the sunny there can be likened to the previous figure 6. I'll flip back to previous figure 6. If you go back to figure 6, here we have 3 states Hidden Markov model. We can readjust this to actually take the observable state. We just added to figure 8. I hope you are getting that. So in essence, what we are saying there is when we add observation states, so the transition states with the initial probability, then we have what is called the hidden Markov. So the word hidden there is telling us that we don't know anything about the sequence that we want to predict. So in speech recognition, this is how it works. Where we have walk, shop, and clean, we are going to have the future, the Mel's. You know, I said the other time that we are going to extract Mel's spectrogram future. That's from the speech waveform, from the audio waveform, which we have saved, either using wave.wave extension, or we use MP4 extension. So when we extract those features will be at the same level where we have walk, shop, and clean. And we now want to decode the sequence, the correct sequence of words. Don't forget that we have used Gaussian mixture model to actually cluster the phonemes present in those features. We have clustered them in groups. So each of them will be represented by transition states within this Hidden Markov model. So each of them will be in the middle. So it means that we are not seeing them. We don't know anything about them. We want to predict them by observing just only the futures, which in this case, the walk, the shop, and the clean. And of course, each one of them will have their initial probability. That's what you call the start probability. So in other words, the word hidden there is actually from the transition state, which is not what open or which is close. Let me use the word close to the observer. That is why it is called the hidden. And of course, it's a Markov model because it's developing on the Markov chain because it's a sequential modeling. So, and of course, from here we said that the sum, it should be noted that the sum of this initial probability is equal to 1. So we can see that here we have rainy and sunny. So we have 2 initial probabilities. So we have 0.3 and we have 0.7. For instance, in figure 6, where we have 3 states, we are going to have 3 initial probabilities. So what we want to look at now is how do we calculate initial probability for speech recognition? Because all these values, all these parameters, they are actually calculated. And even the transition one, the parameter within the transition state, for instance, here, probability of sunny given rainy is 0.6. Probability of rainy given sunny is 0.2. So probability of rainy given rainy is 0.4. Probability of sunny given sunny is 0.8. How we are getting that? So each of these probabilities, there are algorithms that we use to calculate them. For instance, the transition probability, we use what is called the forward algorithm, the backward algorithm, the Pamwich algorithm, because that's what the backward algorithm is actually looking into. It consider the forward and the backward, and use that to update until the best transition probability is obtained for each of those transition paths. So on the next slide, for the Hidden Markov model, we now have additional parameters to the Hidden Markov chain. Don't forget that in the Hidden Markov chain, we talked about the transition probability and the transition matrix. So now we are now bringing in the initial distribution, the emission probability, and the emission matrix. Now, if I may ask a very simple question, why do you think we are bringing in the initial distribution, the emission probability, and the emission matrix into the Hidden Markov model? Who can answer the question? Why are we bringing in the initial distribution, the emission probability, as well as the emission matrix into the Hidden Markov model? Don't forget that what we talked about before was the transition probability and the transition matrix. But now we are bringing 3 different attributes or characteristics to actually quantify or to actually characterize the Hidden Markov model. Who can give us the reason?
Does anyone want to try? Please, can we have someone from online participant this time around, please? Don't be scared to talk. We are all learning. Just say something.
Then,
No. Hello, are we together? Miss Amarachi, are you with us? Engineer PJ,
I'm here, I'm with you. I'm with you and I'm following.
okay, thank you, ma. Okay, so you can continue, Mr. Shobala.
So the reason there is now, because now we have introduced the observation states. So that is why we need to now, we have introduced the observation states and the start probability. So that is why we are looking at the initial distribution, the emission probability, and the emission metrics. So when we look at the initial distribution is very simple. It's actually talking about the probability of each of those states. Probability of raining, probability of sunny. So how do we calculate that? That's what we are going to do after this. So initial probability, so how do we calculate the probability of raining? How do we calculate the probability of sunny? That's in relation to speech recognition. We are going to see that. And of course, the next one, which is called the emission probability. Now, the emission probability there is, when we look at this figure 8, we will notice that each of the observation thing, the arrow is pointing toward them. Like the transition state is what we have at the middle. It's like it's emitting some value, some parameter towards the observation state. That is where the word emission actually comes into play. That's why they call it emission. And of course, it's a probability because it's a conditional probability. So from there, just like what we've been doing before now, I can say the probability of work. What's the probability that somebody will work given that the weather is raining or there is rain? So what's that probability? 0.1. What's the probability of shock that somebody will be in a shock given that the weather is raining? That is 0.4. What's the probability that probably somewhere will be clean given that it is raining? It is 0.5. And we can see that all the red lines that come out of that raining, if you add all the values, all the probability, to give us 1, just like what we have said before. The same thing for the sunny. The probability of work given sunny, which is 0.6, probability of shock given sunny is 0.3, and the probability of clean given sunny is also 0.1. When we add 0.6 to 0.3 and then 0.1, we get 1. So that's
Okay, so for the red line, what does that signify?
So that red line is telling us the conditional probability of work of each of these observation states given raining. That is, what's probability of work that an observer, somebody will work given that the weather is raining.
Okay.
What's probability that somebody will stay in a shop given that the weather is raining? That's 0.4. And the last one there, what's probability that a place is tidy given that the weather is raining, which is 0.5.
Okay, thank you.
So
Okay, so we have another question, Mr. Denny.
I want to be sure that I'm following the sequence since it's a question.
okay.
Okay, so I don't know if I got this correct. you said that for the male spectrogram, if I'm correct,
Okay.
The way the speech is captured in the raw form, is that the male spectrogram is being clustered.
Yes.
Right, with regards to the phenoms.
The phenoms.
Phenoms. Okay. So which means that syllables that sound alike are most likely going to be in the same cluster.
Yes.
And so it's not necessarily that we have a sequence. So if somebody says, I'm going to school, we don't know that the first word is I, the second word is I. We all know that, okay, I and maybe another thing that sounds like I are in the same cluster. Yes. And then things that also sound alike are in the same cluster like that.
Yes.
Right. And I don't know if I'm correct up to that point. Yes. Okay. So how, my first question now would be how does it know where the first thing that was said, and how, since it's speech recognition now, how is the algorithm able to know? Because I was expecting that when you were explaining the reason for the initial probabilities, or something like that. So I want to ask, that would be the first question.
Okay, so what we have there is, actually for the modeling, we have what we call sub-transition states.
Okay.
You get that? So what we have there at the transition states in a normal speech recognition is the phoneme that will be within the states. So the phoneme, from the phoneme, we now have the main states that will carry the word equivalent of those phonemes that will be grouped. So that is where the next part we'll be talking about after this. That's how we transition from one state to another state after a particular time step. Maybe after one time step, after two time step, you cannot generate maybe the word equivalent of set of phonemes that you join together that will not give you a word. It's not that you are just going to have the word equivalent, or let's say a particular word will just be formed immediately. No, it's not like that. Phonemes will be formed first. Then you have word that will be formed next. So that is why we have some, actually in speech recognition, we don't have the transition state representing the word directly. It has to start from the phoneme first.
So you said you will get to the part where we'll look at how it is taken.
After hand states or two states or something like that. But we'll not look deep into the one for speech. We'll just look at how it's done.
My second question would be on the states, which would mean that all the words in a particular, all the words, I want to assume that the words are states in this
Yes.
regard. Okay.
Yes.
So which means that for every speech, we'll already have all the possible states ready. So I'm wondering why we have the emitting part of these states in a situation where we already have all the states captured. So because I was looking at the sense where maybe if you are typing on the phone, we have predictive capabilities where as you are when you type a word, you have the prediction of the next word. So I'm thinking so I was looking at that alongside this. But I'm aware that the topic we're looking at is speech recognition, not necessarily what I'm thinking. So why do we have the emitting? That would be my second question.
So if I get your question very well, for each of the observing, like for instance now, for speech recognition, we extract the spectrogram. This spectrogram is actually a 39 feature representation for each frame. So we divide the speech waveform into frames. So in the end, when we carry out the frequency analysis, we now extract 39 features. So each of the 39 features will serve as the observation state. And it will be a replica or representation of the phonemes together now. So it's not that this is fixed like this, that the observation is fixed. It depends on that particular speech that the person is giving out at any point in time that will not determine the number of states we are going to have. So we are going to see in the later on what we are going to see that, because here we'll be restricting ourselves to 3 observation states. So when you have 3 observations, we are going to give ourselves some observation states. Maybe the mode is happy, sad. So what is the sequence of weather that is replica of that happy sound? Sad. Do you get that? So it's not a fixed parameter. So it's something that is adapted based on the speech that is available at any point in time. And the state itself, the number of states is equivalent to how much, what's the length of, or what's the number of words that should be decoded or that is needed to form a string or a sentence. Do we get that now? I think I've answered your question. Okay.
Okay, Shobola, I think to just add to your explanation, Udeme, you know, for sequence modeling, you also have to factor in temporal dependence. So you are factoring in, so the example you gave, even though you are going to have maybe the same word occurring at different time, having similar frequency or spectrogram representation, but you know they are occurring at different times. So the timing is also a factor. You understand?
Yes, sir.
So which implies that time will be a basis to distinguish between the different states now. From the sequence modeling implies a temporal, you are factoring in temporal dependence. Is that okay? So,
yes,
sir. So I think Shobola, you can go on.
Thank you, sir.
Yeah.
Okay, so Mr. Shobola, you have 15 minutes more. So please.
Sorry, please.
Shobola, are we still together?
Yes, sir.
Yes, sir, they're trying to.
Okay.
Please, few minutes, please. Sorry, please. Sorry, please. So here we have the emission so we have the emission probability. So here the emission probability there is we can see that we can model using equation 3. Emission probability for probability distribution, or emission probability for probability mass function, that's for discrete variable. And why the top one is can be for discrete variable or for continuous variable. And here we have probability of x given z of k. So x there is representing the observation states. X there is representing the transition states. Transition, that's the sequence we want to decode. That is the transition state sequence that we want to decode given the observation states. And here we are saying that the second one says that what's the probability of the sequence being a discrete value equals to x given the observation states, and of course it starts from index 1 up to m. So we'll see an example of that
Sorry, please, we are trying to sort things out. So on the next slide, we have, so we can extract the Eden Markov observation states into a matrix, which is called the emission matrix, which is what we have on the right-hand side there. So we have probability of, so the interpretation of this can be probability of work, given raining, which is 0.1, probability of shock, given raining, 0.4, probability of plane, given raining 0.5, and when we add all the probabilities along the horizontal, we get 1. And we do the same thing for the sunny, we also have 1. So the first hands-on practical which we'll be doing this afternoon is how do we calculate this initial probability? So the approach to calculating the initial probability. So here we have A to be equal to 0.2 is a matrix, is a 3 by 3 matrix, square matrix. So here we can calculate. So here we have on the row on that table 1 we have H representing hot dog. We have P representing pizza. Sorry, H representing hamburger, P representing pizza, and HD hot dog. So here the 3 parameters, they are actually representing 3 transition states. 3 transition states. So the interpretation of the table here is what probability of hamburger given hamburger, which is 0.2. Probability of pizza given hot dog is 0. Probability of hot dog given pizza is 0.7. And of course, if we also sum all the probabilities horizontally, we see that we have 1. For instance, along the horizontal where we have hot dog, we have 0.2 plus 0.6 plus 0.2, which gives 1. And same for the other 2 rows. So how do we do this? So what we do here is we get what is called pi naught. Don't forget that if I go back to the initial distribution, we use pi to represent the initial distribution. From the initial distribution, we can also determine what is called the initial distribution is actually talking about initial probability, same thing as saying initial probability. So we represent initial distribution of probability using pi. So for us to calculate the pi, we get an initial pi. We now fill it with strings of zeros and 1. 0 and 1, 1, like what we have on the next slide here. We have pi naught to be 0, 1, 0. We can use 3 different permutations. We can use 0, 1, 0, we can use 1, 0, 0, and we can also use 0, 0, 0, 0, 1. So what we do there is here we want to calculate the initial probability of hamburger, the initial probability of pizza, and the initial probability of hot dog. Don't forget that the initial probability we are talking about here is not conditional probability. I repeat, they are not conditional probabilities. So how do we do this? What we do here is we take that pi, like the question I have on slide 21, we take that pi, that initial pi, let's say for instance 1, 0, 0, is a vector. So we multiply it by the matrix A. By the time you multiply by the matrix A, you are going to get the result of multiplication. So when we get the result of multiplication, for instance, on the next slide there, when we pick 0, 1, 0 and multiply by that matrix A, we get a new vector 0.3, 0, and 0.7. I believe we know this. 0, 1, 0.
Hello, Shobola.
Huh?
Can you explain how you came by the 0, 1, 0 so that you can carry everybody along?
Yes. So I said that 0, 1, 0 is a value you can pick. You can make your decision on which particular I want to pick. We have 3 different arrangements we can pick. We can use 1, 0, 0. We can use 1, 0, 1, and we can use 0, 1, 0. Sorry, we can use 0, 0, 1, and we can use 0, 1. So it has to be 1. In other words, it has to be 1, 1, and 2 zeros.
Let me say something. So that 0, 1, 0, you have hamburger, pizza, hot dog. That 0, 1, 0 should translate to pizza being the initial states. Do you understand? That's 0, 1. Is that not what that means? That's 0, 1, 0. So either you're exactly, you must have a starting point. You can't have 0, 0, 0.
Yeah.
You must have a starting point. That 0, 1, 0 translates to your initial condition being preserved.
So that is our initial. So I may also decide to say I want to use one.
Exactly. Hello, Shobola. I need you to let people know why your choice of, because the options are, if you want to have a total of 1, there are 3 options. You can have 0, 0, 1. You can have 0, 1, 0. You can have 1, 0, 0. So why did you settle for 0, 1, 0?
Yeah, I just pick at random. You can pick anyone you want to pick. And
It's an initialization, right? So you need to explain that.
Initialization.
So
we can pick anyone. But it also depends on the complexity of the algorithm you are writing. Because, for instance, here, if you try 0, 0, 1, the algorithm will tend towards infinity. It will not give you result in time. But if you try 0, 1, 0, you are going to get this result we have there after 37 iterations. That if you write the for loop, it's going to iterate 37 times to give you the result. So what we now have there is, if you multiply the first place, so the first vector there is a 1 by 3 vector, and the A there is a 3 by 3. So if you have 1 by 3 multiplied by 3 by 3, the result will be 1 by 3. So that's why we have 0, 0.3, 0, and 0.7. So here we have gotten 0.3, 0, 0.7. So we can see that in the first iteration, the result we get here is not the same thing as the initial value. It's not the same thing as the pi naught we have on the left-hand side. So we iterate again. We pick this 0.3, 0, and 0.7. We multiply by A again. We get another result. We get another 1 by 3 matrix. So we keep on multiplying till when the value of pi on the left is same thing as the value of pi on the right. And here, when we start with 0, 1, 0, that will be after 37 iterations. If you write the for loop, you are going to get that after 37 iterations. So, in other words, what we are saying is the result pi naught that we have there to be 0.35211, 0.21127, and 0.43662 is what it means mathematically. It means that value multiplied by A will give us this pi back. I hope somebody is getting that. So that is the meaning of that pi naught. And of course, the arrangement we have initially, we have the first element there to represent the hamburger, the second one to represent pizza, and the last one to represent hot dog. So we also pick them sequentially as they were before, and that's why we have probability of hamburger to be 0.35211, probability of pizza to be 0.21127, and that of hot dog to be 0.43662. I will not say that if you use 100 as your starting point, you are going to get the same results. That's what you are going to get if you write the program very well. So we have a Python code there. So if you write the same result, you are going to get that after 37 iterations. After 37 iterations, that's the same number of iterations, that's what you are going to have. Now, for the second example here, we can see for the second example, we have sunny, cloudy, and rainy. This one is coming from figure 6. This one is coming from figure 6. Maybe we should flip back a bit to figure 6. So this figure 6 here, we have the matrix. We have the transition matrix here in figure 7. So here, this is what we extracted out on the second example here in our table 2 of example 2. So here, if you start, here, I actually started with 100. So if you put this after 33 iterations, you are going to get this parameter. If you try with 010, after 32 iterations, you are going to get this same result. So how do we do this? And of course, we also have on example 3 for 2 by 2 matrix. That's for figure 8, where we have rainy and sunny. Rainy and sunny. You can remember where we have rainy and sunny, and we have walk, shop, and clean. So we have the matrix here. If you also do this, if you start, you can start with 10. So here you are going to have 2 permutations, 10 or 01. So if you multiply 10 by that matrix, 0.4, 0.6, 0.2, 0.8, you are going to get the first result. So here, if you run it after 27 iteration, if you use 1 0 after 27 iteration, you're going to get 0.25, 0.75. After 24 iterations, if you use 0, 0, 1 as the starting point, you are going to get the same result. And please note that the value that we use here is 0.3 and 0.7. They were just picked as abstract. They were abstract values. So the correct value for that is actually 0.25 and 0.75. Please take note of that, please. So how do we do that? This is a Python code implementation of that. Now, this is just here we can see that we have a function there. It says that we have some comments there. It says markup chain to find the probabilities of hamburger, pizza, hot dog, given the conditional probability of each as a transition matrix called Mart's input to the algorithm. So the input to the function is Mart. We use MAT as Mart to the function. So the two functions there, they are the same thing, but it's just that the first one is actually restricted to 3 states. The second one is restricted to 2 states. If we want it to go beyond maybe 3 states, we can write an algorithm that can adjust to any state that we want. But the one we have there is actually restricted to 3 states on the left, 2 states on the right. And of course, so I don't know if we can just practice this together and run the code and see the results. Okay, that will be after. So let's just see the explanation of this. So the way this run is this. So on that function, the name of the function is markup. I'm using the left-hand side. The name of the function is markup, and the input argument, that's just a single input argument, which is Mart. So the first thing that we define a list. So that list there is equivalent to that pi that we defined before, the initial value. So this is a 3-state markup chain. So we have 1 0 0 as our initial value, and here we have q. We are defining the value q to be equal to 1. That is the value that we use to run the while loop. So here we define a list. So that LSC to be equals to open square brackets, PA close square brackets is actually a list of variable in function. In Python, we have lists. We have different types of variable. Variable. We have what's called the list of the string, the dictionary. We have the sets. So here is the list. So we are putting that initial value into that list. So the list as it is there, the LSC as it is there, is having a sub list. So the sub list there is 1 0 0. So if you actually print that LSC before you run that code, if you print it at this point, or you return the function if you return the LSC at this point, it's going to give you a list with a simple sub list. So in other words, the length of that LSC will be equal to 1 at that stage. So we now have a while loop that we start at 1. That q equals to 1, we can use any value. I will get that. We can use any value, we can use true, we can use false. For any value that will negate false, we can use it there to actually commence that loop. So after the first while loop there, we have VAL to equal to LSC of -1. So we are calling that LSC of -1. LSC of -1 means the last value in that list, because the list is having just a single sub list. So then the last value in that list at this point is still 1 0 0. How we attest that? So that 1 0 0. So we now write on the second while loop. On the second while loop, what the second while loop is now doing there is now doing matrix multiplication of that first sublist. Of that sublist from the back of the main list, which is 1 0 0. It's multiplying it by the matrix itself. If you look at the bottom of that function, I have 3 different functions that I'm calling, right? They are all markup chain with different parameters. So the last one I left there is print markup. So here I have 0.6, 0.3, 0.1. So here the length of the list there is 3. I hope you are taking note. The length of the list there is 3. So it means that the list is having 3 sub-lists inside of it. So if I print this particular list, let's assume that I print this list alone as it is here. I'm going to have 3 rows, 3 columns. So on the first row, I will have 0.6, just like the way we have it on the transition matrix. I'm going to have 0.6, 0.3, 0.1. On the second row, I will have 0.2, 0.3, 0.5. And on the third row, I will have 0.4, 0.1, 0.5. So that's the arrangement of this list in Python. If you run this particular, if you print this particular list. So this matrix now, in matrix, you want to do, if you want to do matrix multiplication of 100 with this matrix here, I'm going to pick 100. I will multiply it by the first column. I will use to multiply the first column and add on the value. That is, I will have 1 times 0.6, 0 times 0.2, 0 times 0.4. When I do that, I will add them together. That will give me the first row, first column of that 1 by 3 matrix. I'll have first row, first column of that 1 by 3 matrix. Excuse me, please. So you can also be doing it so that we get to the same, we are doing the same thing together and on the same page. So here, you will see that if you look at that second while loop, the second while loop there, you will see that we call that Mart. That Mart is the matrix. The matrix, the function markup is having an input argument Mart. Now, if you go to the bottom, we say markup and we put the value of the list there. We put a list value there. We put list there. So that Mart is equal to that list. Is equal to 0.6, 0.3, 0.1, 0.2, 0.3, 0.5, and 0.4, 0.1 is 0.5. So that V1 equals to Mart 0, Mart, this is an indexing. We call it an indexing in Python. So that Mart 0 means that it will look for the first sublist. That Mart 0 means it will look for the first sublist, which is 0.6, 0.3, 0.1, and extract H. H there is on the first, this is a while loop. So, and the while loop there, if you look at that curve, H is starting from 0. So it will pick H to be 0 because we don't increment H using H plus equals to 1. So H is 0. So if you pick the first value, which is 0.6, the second one, which is V2, V2 is equals to Mart 1. That is, look for the second sublist in that Mart, which is 0.2, 0.3, 0.5. That's the second row. The second sublist, second row. And pick the first element, 0.2. Then V3 means V3 equals to Mart index of 2. Means that index of 2 means that look for the third row. That's the last row there. That is 0.4, 0.1, 0.5. And pick the first element, which is 0.4. So we have picked 0.6, 0.2, 0.4 of the matrix MAT. So on the next line, we have pad equals to pad of 0, PH equals to pad of 1, PH3 equals to pad of 2. Don't forget that pad is equal to LSC of -1. LSC of -1 is 100. So pad of 0 is 1. Pad of 1 is 0. Pad of 2, which is the PA3, is the last value, which is 0. So here we now do RES1 to be equal to V1 and P1. You understand that multiplication now? That is, multiply 0.6 by 1, multiply 0.2 by 0, multiply 0.4 by 0. Another way we could have achieved this line 3 there, that res1 is, I could have used zip function in Python. So the zip function is going to cluster, it will take 0.6 and 1 together, 0.2 and 0 together, and 0.4 and 0 together. That is corresponding elements at the same index. Corresponding elements or elements at the same index, to take them together, you can now multiply them using list comprehension. So when you multiply all the elements, you now add them. You add the product of each. So when you add the product of each, you have res1. So here you are going to have 0.6 plus 0 plus 0. So you have 0.6. So we now append 6. So we append 0.6 to a list, an empty list, which we initialize as LST. So it means that LST at where we have LST dot append res 1, it means that LST will now be equals to 0.6. Open a square bracket, put 0.6, close the square bracket. I hope that is very clear, please. So there, we now increment h by 1. So when we increment h by 1, the next value of h, that is 0 equals to 0 plus 1. So the next value of h will be 1. So on the next value of h, it's going to pick all the elements in the second column. So we have 0.3, 0.3, 0.1. So 0.3 will multiply 1, 0.3 will multiply 0, 0.1 will multiply 0. So we can see that it is only the V1, V2, and V3 that will be changing. The PAL will always be fixed, it will not change. 100 will always be fixed, it will not change value. So for h equals to 1, it's going to be 0.3, 0.3, 0.1, and follow the same process. And this time around, it's going to be appending the result of 0.3 multiplied by 1, 0.3 multiplied by 0, 0.3 multiplied by 0. So here we are going to have 0.3 when you had the products of each. So you have 0.3. So here we do now do list dot append. That is, initially I have LST to be equal to 0.6. So append means that add it from the back. So I will now have 0.6, comma 0.3. That will be the value of the list at h equals to 1. Then do the same thing at h equals to 2. So if you pick the last column, which is 0.1, 0.5, 0.5. So here, 0.5 and 0.5 will give us 0 because we have 0 that are multiplying there, that's multiplying there. And we have 0.1 multiply 0.1, so I have 0.1. So here, my list will now be 0.6, 0.3, and 0.1 will be appended to it. So now, if you now check, now look at this if function. If LST is equal to 5, I would say that if LST, now the value of the LST there is 0.6, 0.3, 0.1. If it is equal to 5, that 5, who can tell us the value of 5? Anyone following us? That's 100. So if LST is equal to 5, then return the value of that LST. That is when it now give us the value, because at that time that is equal to 5, that's the value, because the condition there is when you use that pi to multiply a and you are getting pi back. The pi you are getting back here is the LST. Are we getting that? So once it's equal to the pi, then I'll put the result for us. Do we get that? I'll put the result. So on the first iteration, it's not output it because it's not equal to the initial value of pi. So here, what if we now do there is I have another list which I have defined. So the list initially, which is PA. So the PA, the LSC that has 100 inside of it, it will now append this 0.6, 0.3, 0.1 to it. So it means that the list, the LSC now will now be having 100, comma 0.6, 0.3, 0.1. So for the next iteration, so val equals to LSC of -1. The LSC of -1 this time around will now be 0.6, 0.3, and 0.1, and follow the same process. So you can see that here I actually intentionally outputted LSC and Q because I needed the value of the iteration. The Q there is the iteration was value, so which we actually we need for this algorithm. And I want to believe this explanation is very clear. And the second one there is for two states in the Markov chain. So you can look through that by yourself. The code will be sent to you. You run it and see. And I believe this is well understood by everybody. So thank you very much for your time.
That's not enough for. Okay, thank you so much, Mr. Shobola. I'm trying to make sure we are still within the scope of this program. This is a tutorial, And we know tutorial is supposed to be different from normal class lecture. So I don't want us to turn this into lecture. I want people to understand what we're doing. So we shouldn't try to rush. You get what I'm saying? So that people can actually know what we are doing. Thank you so much. That was awesome. Thank you. I know if I've given you the time, we can still be here till 9 o'clock. So, but thank you. Yeah, so this is time for questions. If you have questions, please, there is no question that is irrelevant. There is no question that is foolish. Any question at all. Like I said earlier, this is a tutorial. What is the essence of tutorial? To bring, what will I call it now? Is it A-lead students and maybe Z-lead students, everybody together, we're trying to rub mind and we're trying to learn. So please, if you have any question, online participants, please, kindly, maybe you type it, I will read it out for you if you don't want to talk. Then if you want to talk, you can unmute yourself, you can raise up your hand, we'll call you. If you are truly with us, I don't think you shouldn't have any question. Answer about, that was more than 50 minutes lecture. Now, before I come to physical participants, I need to get feedback from online participants, please. We are not going to move on. We're not going to end this meeting if we don't have response from online participants.
Hello, good evening.
Good evening, ma'am. Thank you for bailing us out. Okay.
Yes, ma. I don't have a question. I just want to say that I'm very grateful for the presentation. It was quite fast, actually. I was struggling to keep up, but at least I was able to pick one or two things. So thank you. It's just a comment I have.
All right. So sorry about that. Yeah, but thank God you were able to pick one or two things. Yeah, that's the idea. Do we have any other observation? Do we have, yeah, so from this observation, it's going to help us moving forward. So please, if you have observation as well, please don't be shy. Talk. We're here to rub minds, we're here to learn together. Yeah, so we have someone bail us out already, so I can actually free the online participants now. So to physical participants. Yes, sir.
Okay, thank you very much. My question is, I want to refer you to the slide that we performed 37 alterations?
Yes.
Yes, sir. So I'm interested in the final result. Now, my question is, can you say this, after performing 37 alterations, can we say that the sequence or this hidden Markov model has attained a stable state? If it does not attain a stable state, at what stage can we say that the probability matrix has attained a stable state? That's my question.
So we say that once that pi naught A is equal to pi naught, then at that point, we can take that value as our initial probability. So it's a convergent state, it's a stable state. So once we have that condition, so what we are saying there is that 0.35211, 0.21127, 0.43662 is the same value we have on the left and on the right hand side. So in other words, what we are saying is we have 0.35, let me just speak to 2 digits, 0.35, 0.21, 0.43, multiplied by 0.2, 0.6, 0.2, 0.30, 0.7, 0.50, 0.5 equals to 0.3, 0.21, 0.35, 0.21, 0.43. That's the interpretation.
Okay, thank you so much, sir. Mr. Dare, you were raising up your hand.
Thank you so much for that presentation. I have, okay, forgive me, I think I'll take us back a bit. No, that's slide.
Yes.
No, the iteration slide, that's where we have the pi naught A matrix.
Yeah.
Yes. I want to understand how we get to do the iteration that we have the values to be the same, because looking at that equation directly, that A should, for that condition to hold, that A should be an identity matrix.
No. We are not looking at identity this time around. Yeah, it's like an identity map, but it's not from that angle that we are looking at it. It's just the pure mathematics. If you want to use hand, you can't use hand to do this thing. You have to run the program, because the list I've come across so far is the 22 iterations. If you run it the first time, run it the second time, run it the third time, until it reaches 37 iteration, that is when to converge to that same value that you have on the left, you also have on the right. Iteration, you won't even know, you just continue doing it, you just continue doing it. But if you run programs within just 5 seconds, you've gotten your results.
Okay.
It's not something you can do with your hand. Except you are so lucky that part, I've not come across anyone that you can just do it like 3 times and you get them to be equal. It's not possible.
Okay, thank you, sir. I still have one question, please. Forgive me. I am trying to understand this. If we multiply that matrix A and matrix B, we have a result. If we multiply that pi naught and A, we'll have a fixed result.
Yes. No. What we are saying there, actually, the heyday is like an identity. Because when you say something an identity, mathematics is what can I multiply with this to get the same result? So anything that makes you get the same result of what is an identity. So, but here it's not a pure mathematics. So you keep on the A, that A is a transition matrix that we extract. Is a transition matrix. It is fixed, it does not change. It is the pi that will be changing. We start with an initial value of pi to be 0, 1, 0. We can also start with 1, 0, 0. So if we start with an initial value of pi of 1, 0, 0 and use it to multiply that fixed value of A, you are going to get your first result on the right hand side. You get that? If you use 1, 0, 0, for instance, now you're going to have 0.2, 0.2, 0, 0. Yeah. You are going to have 1 times 0.2, you have 0.2, right?
Yeah.
Oh, sorry. You are going to have 0.2, 0.6, and 0.2. That's what you are going to have. You get that?
Yes, sir.
That's the first value. So that 0.2, 0.6, and 0.2 that you have is not the same thing as the pi on the left hand side. So you pick that 0.2, 0.6, 0.2, use to multiply A, it will replace that 1, 0, 0 you started with.
Okay.
So you keep on multiplying till when that what you have on the left the same thing as what you have on the right. That is when you stop.
Thank you, sir.
Thank you so much, Mr. Dare. Do we have any other question in the house?
Thank you very much, Engineer Shobola, for the clarifications you're bringing to some of the questions that we have. My question would be directly towards one of the things you mentioned earlier about the choice of the initial values. You said that you chose 001, if I'm not mistaken. There was a particular
random,
yes. There was a particular one you chose, and you said
if you use 001, for instance, because I ran the program.
Okay.
Use 001, it will not give you results. It will just a hand.
Okay, so
infinity.
My question would be, how do we explain that?
So it means it's not an optimized initial value they are supposed to use to run it. But it's not in all cases. Okay. I actually tested it on some others as well, where it worked. But on this particular one, if you try 001, it will hang.
Okay. So
the program will not give you outputs. You get that? The program will not give you outputs. It will just hang there. It's like to be like you are expecting something. but it's not come.
Understood. I just wanted to know if there's an explanation behind
So
that.
it's just not, what it means is not an optimized initial value you are supposed to use. You can just look from other values.
If we use some other combination and it gives us an output, are they going to be the same?
Of course, you must get the same value. Yes, if you use 1, 0, 0 or 0, 1, 0, you must always get the same thing. It will, if you write the program very well, it will always give you the same thing.
All right,
yes.
thank you so much.
Okay, so do we have any other questions?
Another thing again, you should take notes to be sure your answer is very right. Is the sum of all the items you have there must be equal to 1. That's the confirmation that what you have written is very correct or valid.
Yeah. Thank you, sir, for that presentation. So we talk about how to that we first calculate the initial probability, initial state probability. Then we move to the transition probability. So my question is, after I've gotten the transition probability, how do we now combine these to get the observation itself to compute the probability of the observation?
So if you want to calculate the observation probability, for instance, we've not actually gotten there. So that is where I talked about, let me just show us this. That is where this comes into play, the Baum-Welch algorithm. So the Baum-Welch algorithm, let me see. Oh, I don't have it. So the Baum-Welch algorithm is where is what we use to actually calculate some of these probability. So the Baum-Welch algorithm, we actually calculate the transition probability, the emission probability, and update it for you. But at the same time, we can still use, if it is transition probability, we can just use what we have done here. We've not even calculated transition probability. If you want to calculate the transition probability, replica of that speech, that's the observation state. That's where you now use the Vitavi algorithm. But if you want to calculate other probability like your transition, like your emission probability and the likes, or you want to update the system such that you get a particular transition probability or observation probability that is suitable for that transition state or the emission state, that is where the Baum-Welch algorithm actually comes into play.
Well, we've not gotten there, right? Okay, so I think it's wise to wait till we get there so we can all catch up. Thank you. Okay, so the last question.
Okay.
Presentation about the iteration. I want to ask a question. The iteration is how many times the loop turn to find the good results. Is that?
No, as long as you have not gotten the same value of pi on the left and right, the loop keep on looping. Yes, iterating. So once you can see that on that program, I actually put a condition there. The condition there is if LST. So if LST equals to pi, that is the condition there. Because if I don't put this condition there, it will keep on looping to infinity.
My question is, if we found for the specific matrix that we use to calculate, if we found, for example, for T iteration, and we run we choose another unit matrix, and we found less than this before iteration that we found, we choose this. Okay. You choose what we found?
No, I don't get your question.
Okay, so what she's trying to say is that that place we're using 001, 010. So let's say, for example, the first one we use was 010. Okay. Then maybe it's got that state that will work after 37 iteration.
Okay.
Then you now use 100, and it also get the same result maybe after 20.
Yeah, it's possible. So sometimes you might have the same iterations, the same number of iterations for different initial conditions. And sometimes you can have the same, like what I have here. I have.
Yes.
Okay, I know it depends on the complexity of the algorithm. if you have to pick the shorter one as because you need algorithm that is very fast.
Okay, and we can compare the exactly. And
Yes.
can we compare the iteration to an epoch? Is it the same thing?
Say what? Epoch. Yeah. It's iteration is same as epoch.
But
Yeah.
the epoch is it's train our model to learn, but
to
find good results.
But I would say because when you look at epoch in machine learning, it's actually like an iteration. But here we don't use the word epoch. Epoch is a word that is restricted for machine learning, but it actually means iteration. But here they use it. It's also a learning tool. It's also a learning because you are trying to achieve a particular value. So you keep on multiplying, keep on learning till you get a value that such that what you have on the left is same as what you have on the right. So it's still equivalent of epoch, but we don't use that word epoch here.
Our master of events, I think time.
Yes, we are done, sir. I was
This is
about to
sounding-
call you for the closing remark before we say the closing prayer, sir.
Okay. So am I giving permission to go ahead?
Yes, please, sir.
But it's as if everybody wants the discussion to continue. I didn't
No,
know
sir.
because the live that came up after the presentation is actually amazing. So really, really impressive. Well done. Well done, Shobola. I think everybody will agree with me that he just laid the foundation for where he's going.
Yes, sir.
Exactly. So please put that in mind. If you look at the topic, it's actually sequence modeling with a recurrent or sequence modeling anyway. Of course, we have different variants, which Dr. Oshi also mentioned at the opening part of this lecture. So, but the reason why he wanted to lay the foundation from the statistical point of view is for you to know where the journey started. Okay, and it's a very good one for research, because by the time you now come to the cutting edge, maybe architecture, neural network, maybe architecture or model, it's also a good.
We can't hear you, sir. I think the network.
Shobola starting this way. For me, it's
Hello, Prof.
a beautiful one. Okay. And the way you have the mathematics, it shows that persons within the audience, they are not scared of the mathematics. Meanwhile, I was thinking you will get to a stage where you map the speech, automatic speech recognition, which was your maybe anchor use case. I was thinking you were going to map it with the different component of HMM, the state, the observation, the transition probabilities, the emission probabilities, and the initial probabilities. So let me assume that you have only laid the foundation in this class, and that most likely you are going to require, is not even most likely, is looking like you will need another class in order to do justice to where you started from, because that is when persons in other research domains, that is when they can even see how HMM is applicable to what they are doing. I love the idea of somebody relating it to you are using epoch to train the parameters of your machine learning models. Okay, so those probabilities are actually parameters for HMM that are also trained the same way you have backpropagation algorithm in machine learning. You have the Fitabi and the other algorithm for HMM in order for you to come up with optimal parameters, the transition probabilities, the emission probabilities. And of course, I'm sure in the next class, Shobola will tell us, with respect to speech recognition, what does the state actually stand for? And what does the observation actually stand for? Because that is when you are bringing it to where the student will be able to apply what you are talking about. So I want to commend the effort. And I don't know if Shobola has one or few words to say with respect to moving forward from here, as well as maybe Dr. Oshin, as the case may be. Hello? Okay, I'm not hearing anyway.
Hello, sir.
Okay, go ahead.
So we've not actually touched, it's just like 20% of what we have.
What
We've
you
not
have
gone
to, apparently.
Yes, sir. So we still have the vital V algorithm part, the forward algorithm, and how to transition
forward,
from
backward algorithms.
one state
Okay.
to another state after a particular time step. That's the way they do it for the
In fact, what we need to do in the next
next class, we'll be starting with how to transition from one state to another after a particular time step. And from there, we'll go on to the vital V on how to decode the maximum the sequence with the maximum probability. That's the sequence
So
that's
for me, okay, thank you, Shobola. For me, I think maybe by your next class, try to bring up the speech recognition use case now. Then you now use that use case, you understand, to illustrate exactly. So that is when it becomes kind of handy for persons to see, okay, this is how I can apply the HMM concept. Is that okay?
Okay,
Then
so
I'm sure that is even not going, it's not going to end there. You will also move to the use of neural networks now to solve the same problem. And now we are able to compare, okay, what was HMM able to achieve? Then what is the different variant of recurrent neural network? And even up to transformer is able to achieve to solve the same
yes,
problem.
I actually wanted to look into those attention mechanisms and position encoding.
No. The way you started is okay.
Yes.
Yeah, the way you have started is okay, but that is the bigger picture. Is that okay? So that's just my take. Then the ME, does anybody want to say anything?
No, not at all, sir. We were trying to tell you to put on your video earlier when you started talking, but since you're done.
Yes, I think I'm done. But to also mention that we have some of our experts in the house. Dr. Taufik has been with us. Dr. Isaac Samuel, the HOD of EIE, also connected to this event. So they may just want to say one or two words before we round up finally. I think we need to recognize their presence. So permit me to, Emmy, please kindly allow them to say one or two words.
Dr. Taufik, please can you unmute yourself and just say a word or two, sir? Thank you for joining us.
Hello, good evening, everyone.
Good evening, sir.
Yeah, thank you so much. I would like to commend the presenters, both Shobola and Dr. Shin, for a very well presented work that they have done. And Shobola, we are all eager to see how you will extend your presentation and your work to the issue of the speech recognition that Prof was mentioning. I'm quite interested in that. So we hope to see you in the next workshop. Thank you so much, and enjoy the rest of the evening.
Thank you so much, sir. Also, we have our HOD Electrical and Information Engineering, Dr. Isaac Samuel. Thank you so much for joining us, sir. If you're there, please can you unmute yourself and just say a word or two, sir?
Yeah. Thank you very much, the ME. Sincerely, I'm sorry for coming late. I missed Dr. Oshin's. But the one I met is heavy. Shobola, well done. We are looking forward to see you extend that work into speech. Very, very important. I'm eager. I've spoken to you about that. By God's grace, going to be one. I think I will find time to also join this presentation here. All the same, I want to thank the center leader, Professor Adetiba for this. This is what we expect to keep students engaged and knowing the real thing, foundation for what we are doing as thinking, getting them to modeling mathematical foundations. So thank you for the good work. Every member of the center, well done, students. We also did well. Really believe that educating ourselves. Thank you very much. Bye.
Okay, thank you, HOD.
Thank you, sir.
Yes, sir.
The Prof, sorry, Prof. I just want to mention again that please, the organizer should ensure that these recordings and subsequent ones are uploaded as soon as possible, so that people can always relate with it as a to refresh what they have learned. If this has not they are not made available immediately, it might go off their thinking or strategy or so. So please, let's always try to upload this thing as soon as possible, including making those codes that Shobola was talking available, so that people can also get their hands dirty and experiment with whatever they are interested in. Thank you so much, sir.
Okay, thank you, Doc. And I'm sure Dr. Oshin and Comfort have noted that. So we'll do the needful to ensure that happens. Okay, so over to you, Comfort.
Yes, thank you, Prof. Thank you so much. So we've come to the end of today's tutorial. We started with prayer and we're going to end with prayer. So can we have Julius take us in the closing prayer? Thank you.
Let's close our eyes for prayer. Father, we thank you, we give you glory. We thank you for our name today. We thank you for our facilitators. We thank you for the students, both on site and those online. Father, we say, be thou exalted in Jesus' name. We pray that everything that we have learned today, we are going to make use of it to advance the course of our research in Jesus' name. For in Jesus' name, we pray.
Amen. 1 minute, online participants, 1 minute, please, before you go, please, if you can, kindly put on your video. So we want to have a normal photograph. Please, just 1 minute. Online participants, kindly put on your video while we take the picture. Just 1 minute. Use anybody's phone. Thank you. Oh yeah, please come. Bend down if they cannot see you. Oh yeah. Leave that, it's not yet. Please now. Don't block my TV. Thank you so much. See you next month. Bye.
Bye.
Okay, bye-bye, everyone. Dr. Taufik.
Sir, Gabriel.
It is well.